Hello everyone. So in this video, I'm going to go over again the conformation of cycloalkanes and also mix that with some concepts we have been learning in chapter 3. And also I want to use the new 3D program that I think is going to be very helpful for you guys to see these molecules in 3D. So very briefly, as a reminder, I'm going to talk about the uh, cycloalkanes and briefly I'm gonna just also talk about their conformations. In order to do that, as I said, I want to use this 3D program that I think is gonna be very helpful. So as we saw in class before, the simplest of the cycloalkanes is cyclopropane. So cyclopropane is an alkane. It's a saturated hydrocarbon having 3 carbons. So we can see here, okay? 3 carbons and 6 hydrogens, okay? So that's the smallest of all the cycloalkanes. And as I said before, because there is only 3 carbons, you can see how the dihedral angle here in between C-C bonds must be 60 degrees, right? And that actually makes these cycloalkanes to have a very high angular strain. So that's one big feature about them, which makes the molecule not that stable. And in addition to that, as I also said before, since this 3-member ring is forced in these conformations, there's not really that many options. So you can see how, and here you can see very much better, how in this carbon and in the carbon in the back, the carbon-hydrogen bonds are eclipsed to one another. So you can see the front here, and there is also CH in the back, which is eclipsed to the one in the front. So because of the 3-member ring conformation, there is a lot of angular strain, and there is also a lot of torsional strain. There are 6, so 3 pairs of hydrogens that are eclipse to one another. That brings a lot of torsional strain to these rings. Because of that, cycloalkanes, cyclopropane is a highly energetic ring, and you can imagine why then organic compounds with containing 3-member rings will be much less stable, okay? Because once again, the angular strain and the torsional strain. The next member is the cyclobutane, and as I said before, also cyclobutane is a 4-member ring carbon. So similarly to the case of cyclopropane, in this case, the molecule has a pretty high angular strain. The angle here in between the CC bonds is close to 90 degrees, and that brings a lot of angular strain. And then there is also the same case as before, the torsional strain that is present because of the eclipse conformations in the hydrogens you can see over here. Okay, the one in the front being eclipsed to the ones in the back, and down here, same thing. Sometimes cyclobutanes are known for having conformation in which 2 ends of the carbons basically they lift a little bit out of the plane. I'm going to show over here what that is. So 2 carbons, these 2 are a little higher. You won't be able to see it much very well here, but you will see the picture in the book. So that actually alleviates, so in the lifting these 2 from the plane of the molecule will alleviate the torsional strain, but will also bring some angular strain to the picture. So that's why also cyclobutanes are not that stable. Obviously, they are a little better as compared to cyclopropane, but still, they have pretty high energy. The next member of the cycloalkane family are cyclopentanes. It's 5-member rings. So in this case, if cyclopentane were to be absolutely flat, then the angle will be a little better as compared to cyclopropane and cyclobutane, but then you will have a lot of torsional strain. So to compensate for that, what you have in the conformation of a cyclopentane is one of the carbons, in this case, this number here, will be slightly lifted out of the plane of the molecule. By doing so, and I'll show you So by lifting one carbon out of the plane, what the result of that is, once again, the molecule is, you can see over here, right? What I mean by lifting one carbon out of the plane, the result of minimizing torsional strain of this CH bond with a CH bond of the carbon next to it. So you minimize torsional strain by achieving this envelope conformation, but at the same time, you increase a little bit of the angular strain over here. That overall effect, the net is much better energy for the molecule. But again, there is a considerable amount of torsional strain here, and there is some degree of angular strain. Once again, because you have more carbons, and then the angles are allowed to be closer to 109.5, these cyclopentanes are way more stable as compared to cyclobutane and to cyclopropane. Okay, so the next member of the family are cyclohexanes. As I said before in class, cyclohexanes are uh, 6-member rings, and the most stable conformation of a cyclohexane is the chair. Okay, so you can see here that this is the chair conformation. Okay, so I'm gonna color code these hydrogens out so you can see better. Okay, so here is a carbon. Behind we have another carbon, 3, 4, 5, and 6. Okay, so that's a cyclohexane. This is a chair conformation. We call this a chair because, as I said in class, here we have like the back of the chair, here we have the seat of the chair in this plane, and here we have the leg of the chair. Okay, so in each cyclohexane chair conformation, there are bonds that we call axial bonds, which are basically pointing up or pointing down, and there are equatorial bonds, which are to the sides. As you can see, if you draw a plane across here, the axial here is above the plane, and the equatorial is below that plane. The plane goes across, once again, the back of the chair. And the same happens for every axial and equatorial bond in the chair. So I'm going to rotate it over here so you can see. If I rotate it over here, the carbon next to it. So as I also said in class, axial bonds alternate. So here we have the carbon in the back has the axial going up. The next carbon has the axial pointing down. The next carbon has the pointing up. The next carbon has the axial pointing down. The next one have it pointing up, and the one in the back have the axial pointing down. Same thing as equatorial. This equatorial is pointing up, is above the plane, and the next one, the equatorial, is below the plane, and the next one, the equatorial, is above the plane. One of the things about cyclohexane that is pretty remarkable is that because of these alternating bonds in between axial and equatorial in carbons that are next to one another, you can see how, first of all, and here you see a lot better, right? So there is no torsional strain whatsoever. Look at these two carbons that are next to one another. So the dihedral angle in between this carbon hydrogen and the one in the back here, this is 60 degrees to this one too. So basically, you can see how this looks like pretty much an stagger conformation in which there is no torsional strain. So there is no torsional strain on cyclohexane because of the dihedral angle here being 60. Remember, in eclipse, the dihedral angle is 0. Okay, and in addition to that, the 6-member rings allows for this ring to have a bond angle very close to 109.5, which makes it trying to show you better over here. So the angle in between each carbon here is very close to 109.5, which is ideal for the hybridization of this carbon, which, as you know at this point, is sp3 tetrahedral structure. So every bond here is very close to 109.5 degrees, so that makes a perfect bond angle, and that also explains why in cyclohexanes we have a very low amount of angle strain. Okay, so there is no angle strain, there is no torsional strain. So what can make a cyclohexane less or more stable? So the last factor that we need to see here is the static strain. Okay, so when do we have static strain in cyclohexane? So as I said in class, something we call 1,3 diaxial interaction. So this is carbon 1, this is the one on top, right? So 2, and this is carbon 3. And on the other side, we can say also 1, 2, and this is carbon 3. So we say 1, 3, right? Because it doesn't matter which way it's carbon 3. So in carbon 1, there is an actual pointing up. In carbon 3 here, there is an actual pointing up. In carbon 3 here, there is an action pointing up. I'm going to try to rotate this, see if you guys can see better. And so here you can see much better the 3 actuals pointing up. And here you have the 1, 3 interactions pointing down, same thing, okay? So what happens is when everything is hydrogen, so if hydrogen here, and if I were to have a hydrogen here, which in this case is a hydroxyl, but when everything is hydrogen, because its hydrogen is so tiny, you see that there will be plenty of space for every atom up there, so there is no static strain at all. However, when there is a group different than hydrogens, now the space start to be a little crowded, and that brings what we have defined as the 1,3 diaxial interaction, which is an aesthetic effect. So the 1,3 diaxial interaction is happening between the atom here that is oxygen is much bigger. In addition, it has a hydrogen, right? So this interaction over here is a 1,3 diaxial interaction, which is destabilizing, okay? So anything that is different than hydrogen in a chair would never want to be axial. I also say in class that chairs, cyclohexane chairs, are always in equilibrium with a flip chair. Okay, just copy the structure over here, and I want to show you what that is. So I said that in a flip chair, this carbon will be, which is the leg here, will be the back. This one, which is the back here, will be the leg. I also said in class that anything that is axial in one chair, it will be equatorial, and vice versa. Anything being equatorial will then be axial. I'm going to color code this hydrogen over here, this one over here. So you guys can see, I'm going to say that's, for example, a bromine. So, okay, so, and one of the things about this program that I love is how the size of the atom is reflecting on the picture. You can see how bromine is so much bigger than the carbon, right? So anything that is, this is an equatorial in a flip chair will be axial. Anything that is axial will be equatorial in the flip chair, okay? So what I'm gonna do is this structure on the right is just a copy of the one on the left. I'm gonna now build the flip chair in the structure of the left. I'm doing here, you see when I did this, I click on minimizing the energy. You see how this bond increases because bromine is much bigger, so the bond length here is much bigger too. So that's something that you guys need to take into account. It's beautifully shown in the program. So what I'm gonna do now is I'm gonna just try to show you here once again the flip chair so you can see how is it built, okay? So to flip the chair, this is carbon 1, which is this one over here is the same. What I'm gonna do is just bring this one up. I'm sorry. So I minimize the structure, so now the bond is much bigger. And what I'm gonna do now, I'm gonna try to just build a flip chair. So bringing this up, okay. I'm minimizing that structure. I brought this up. I'm gonna rotate it so you guys can see what I did. But it actually didn't move, so you can see how this is still in equatorial is the same thing. So let me try again. Oh, sorry. I'm learning to use this program, so let me see. if I manage to do it. This is something that, as I said, you can do at home much better with molecular modeling kits. Okay. Um, okay, it's not working. So I'm gonna try, instead of doing that, I'm gonna try to move down this hydroxyl group and see if that works better. Okay. So what I did in this case, and that was because of, again, you can do either way. I'll show you now, 1 second. So what I did so far, okay, and this is a very good example of that. What I did from here to here, and sorry about if some of you found this a little confusing, just gonna sometimes. So, but this is a good, I managed to do what I wanted to do for now. This is like an intermediate step, okay? And I'll show you now in the slides. So what I did here was, I can actually, let me flip it so you can see better, even better. Okay, so here it is. Okay. So what I did was, look at this. Let's see if I have the proper view here. Here it is. So what I did here was, here is a chair, right? The carbon hydroxyl is axial. Carbon bromine here is equatorial. Okay, so to make a flip chair, I took this carbon here and then pull it down, and I reach this conformation, which is a twist boat. So in this conformation, you see how these bonds, these CH, are very close to one another, okay? So there is a lot of 1,3 diaction interaction in the twist boat. That's why a twist boat is so high in energy, and it's basically um, a transition state in between the chair and the flip chair, okay? So I pull this down over here, reach the twist boat, which is right here, and now what I'm going to do is try to pull then this up to reach the flip chair conformation. Let's see if I am able to do that. So what I'm going to do is I'm going to copy this structure so you can still keep seeing the flip boat. Okay, so here is a twist boat, as I said, and now we're going to try to convert the twist boat into the flip chair. Okay, so twist boat, same as here. We basically only pull this down, and then I'm going to try to pull this up and see if that works. Okay. Oh, I'm sorry. Sorry, guys. So it did work, but I made a little mistake. So I'm gonna repeat it for you. That way you can even see better. So once again, this is the twist boat. Gonna put this one on top here so it doesn't bother me again. Okay, so you can see even the energy. So we have a chair. Once again, pulling this one down, reaching the twist boat. You see the actual interaction in the twist boat that makes it much more higher in energy, and to convert, I'm sorry, a twist bolt into a flip chair, what I'm going to do is to lift now the other end, in this case this end over here, and now I'm going to just rotate it so you can see better. Here it is. Okay, so this is perfect. So look now. Okay, chair. Okay, axial, axial down, up, down, and up in the back. So axial and equal, axial pointing up and down, alternating. This actually is above the plane, this equatorial below the plane. Okay, so above the same plane, you also alternate axial and equatorial. So above the plane axial, above the plane equatorial, above the plane axial, above the plane equatorial, above the plane axial, above the plane equatorial on the back here. Okay, so flipping the chair meaning bringing this down, you achieve the twist bolt conformation, which is highly energetic because of the 1-3 direction interaction over here, and then lifting the other end. So whatever was the back is now the leg, and whatever was the legs is now the back. And as I said in class, anything that is axial in one chair will be equatorial in the flip chair and vice versa. This carbon hydroxide group is axial here. In the flip chair, you can see how it's in equatorial position. This carbon bromine here is equatorial. In the flip chair, it's axial. Okay, so the 1-3 diaxial interactions are the ones deciding the energy of each chair. Remember, if you have two cyclohexanes that are only hydrogen substituted, so simply cyclohexanes, both the chair and the flip chair will have the same energy. You will have 50% of each conformer. But when you have substitutions in the cyclohexane, now it's a different story. Okay, now the chair and the flip chair are not equivalent anymore. The favor conformation will be the chair conformation in which the amount of 1-3 diaxial interactions is lower. In a case like this, these two chairs have similar energy because in both positions there is a group in action, in this case carbon bromine, in this case carbon hydroxyl. If you were to ask me, is the equilibrium 50-50? I would say no. The reason for that is because the hydroxyl group has much larger volume as compared to bromine. Okay, so the 1-3 diaxial interactions here are higher. In addition to that, you can see, and this is beautifully shown in this program, the carbon bromine here, because bromine is bigger, carbon bromine bond is longer, which actually minimizes because now bromine is farther, the diaxial interaction with the hydrogens. So I could say that the preferred conformation for 1-4, so 1 bromine cyclohexanol, this would be the name of the compound. So the preferred conformation would be the one having the bromine axial and the hydroxyl in equatorial position. So if I am asked to draw the most stable conformation of this compound, you would certainly draw this because this is the chair conformation in which you have a lower amount of 1-3 diaxial interactions. And this is the same analysis that you will do every single time when you're analyzing chair conformations. So you basically look for the chair having the lowest amount of 1-3 diaxial interaction. And that will be the favor conformation for that compound. Okay? So I'm going to show you some other examples. Moving now to the slide now that you saw much better in 3D, the transition in between chairs and flip chair and so forth. I'm going to move to show you now. So this is what I said about the cyclopropane. So once again, this is the cyclohexane that I just showed in the program, right? So remember, axial pointing up above the plane, equatorial to the side below the plane, and then you alternate axial pointing up and down, up and down, up and down. Equatorial, same thing, down, up, down, up, down, up. Okay, down. So you need to be very familiar on how to draw cyclohexane chairs and flip chairs. Okay, as I mentioned before, it is important to understand that 6 equatorial bonds you will have in every single chair. 3 of them, 1, 2, and 3, will be below the plane. The other 3 will be above the plane. And the same thing with the axial. 3 will be pointing up and 3 will be pointing down. The more you draw these molecules, the more familiar you will become in uh, understanding the 3D structure of them. Okay, so and then now this is simply just showing you that anything that is, so every shear conformation will be in equilibrium with a flip shear. And as just showed, that transition goes through a twist boat, which basically means that anything that is equatorial, you see the red bonds here are all equatorial. So building the flip shear means like bringing this carbon on the leg here up, so it becomes the back, and then the back bringing it down to become the legs. And the moment you do that, anything that is equatorial will become axial in the flip shear, and anything that is axial, in this case the blue groups, will become equatorial in the flip shear. Okay, it is important for you to really be very familiar to convert chairs into flip chairs and understand where each group goes when you transform a chair into a flip chair. The transition, as I said, goes through a twist boat, and this twist boat conformation is highly energetic because of 1,3 diaxial interactions and torsional strain. Also, you see how these two bonds are eclipsed to one another. So if you were to have, as I said before, if you were to have a conformational analysis of a cyclohexane, you will basically have on one end here a chair, in the other end here in the low minimum for the energy, the flip chair, and in between then you will have the boat and the twist boats as basically transition states in between two chairs, as I showed you guys before. So once again, guys, remember, now that we know this, you ask a question: which conformation is the most stable of a cyclohexane? That's a conformation where any substituent on the cyclohexane is in equatorial position. So you have to basically minimize the 1,3 diaxial interactions. Okay, so here is methyl cyclohexane. So there are two shared conformation for methyl cyclohexane. One shared conformation, you will have the methyl group, which is bonded to this carbon in equatorial position. In the flip chair, bringing this up, this down, now the methyl group will go from, once again, it's still above the plane, but it's going from equatorial. Now above the plane is still, but axial. This is something that is important and I wanted to emphasize. The position in the plane above and below does not change when you flip the chair. Only thing that it changes is it goes from axial to equatorial and vice versa. Anything that is above the plane will still be above the plane. Anything that is below the plane will still be below the plane. This methyl group here in this position is equatorial above the plane is right here, above the plane. When you flip the chair, now it's in axial position, equatorial to axial, and it's still above the plane. What happens in the flip chair is now that the methyl group will have the actual interaction with the two hydrogens. So that brings a lot of static strain to this chair conformation. Because of this, methyl cyclohexane will be in a chair conformation in which the methyl is in equatorial position. So most of methyl cyclohexane molecules will be in these conformations, and very few of them will be in the flip chair because this one is way more energetic. Okay, so remember, everything hydrogens, both chairs are equivalent. The moment you have substitutions, the chairs might not be equivalent, and you need to determine which of the chairs is the one with a lower energy, the one with a less amount of diaxial interactions. So once you know this, and I will give you problems so you can practice this, I also wanted to use these chairs and cyclohexanes to introduce a concept that we discussed in the previous class, which is stereoisomerism. So remember, we defined before isomers as compounds having the same molecular formula. Then we defined constitutional isomers as compounds having the same molecular formula and different connections in between the atoms. Now we're seeing compounds which have the same molecular formula, the same connection, but they have different orientation of their space. And we name these compounds as stereoisomers. Okay, something we already discussed. Stereoisomers, as I said, are two compounds with same molecular formula, same connections, and different 3D structures. So one type of stereoisomers are called cis and trans isomers. And these are stereoisomers resulting from the relative orientation of groups, which are bounded either to the ring or to a carbon-carbon double bond, which we will see later on in alkenes. Okay, so let's see what is cis-trans isomers in the context of cycloalkanes. Okay, so here we have 1,2-dimethyl cyclopentane. Okay, cyclopentane carbons, 1,2-dimethyl cyclopentane. The compound on the right is also, according to this nomenclature, 1,2-dimethyl cyclopentane. However, you can see how the 3D structure of these two compounds is different, where in these compounds you have these methyl groups below the plane of the ring, and this compound is above the plane. If you try to superpose these two, you will see that they are two different compounds. So to differentiate them, for now, we can call them cis or trans isomers. Cis refers to the bulky groups being on the same side, on the same plane, whereas trans refers to the bulky groups being on opposite sides. Okay, one major skill that I mentioned in the class is to be able to transform these 3D structures into flat structures. And remember, in order to do that, you look at the molecules from top. Okay, so if we look these molecules from the top here, you will see how the methyl groups will go away from you. That's why to draw this as a flat structure, we basically draw the flat cyclopentane. We position the methyl groups at the proper carbons. In this case, we know there are one here and there is one here. And now we give the proper 3D dimensions. So looking from top, this will be away from us, so we use a dash. Same thing here. If we look from top, we know the methyls are in this carbon and this carbon. One methyl group will be coming toward us. That's a wedge bond. And the methyl group going away from us will be assigned a dash bond. So you see how these two compounds are two stereoisomers. They have the same molecular formula. They have the same connections in between the atoms. Okay, the methyl groups are bonded to the same carbons, but they have different orientation in space. In this case, we call this the cis isomers because both groups are on the same side, and this is a trans isomer because both groups are on opposite sides. Okay, you can also tell at this point, because we went already over stereochem, that these are two stereoisomers that are not a mirror image of one another, so we can classify them as diastereomers. Also, I wanted to define here what an stereocenter is. An stereocenter is an atom. Mostly in this class we will see carbon atoms, about which if you exchange groups, you will produce a different stereoisomers. So if you look at this carbon over here, if you exchange the orientation of two groups, in this case methyl and hydrogen, so we put the methyl up and the hydrogen down, then you will produce a different stereoisomers, in this case a trans. So this is an stereocenter. Same thing happens here. If you exchange the position of the methyl and the hydrogen, you will get a different stereoisomer. So these two are stereocenters, and these two are also stereocenters. And also, I wanted to define what is the word configuration. And configuration refers to the arrangement of atoms about an stereocenter. Okay, so we will see that in the next video. I will go deeper into chiral centers and configuration of carbons. So here is another example of how to draw these molecules in flat structure and how to analyze their conformation. Okay, so here we have 1,4-dimethyl cyclohexane. This is also 1,4-dimethyl cyclohexane. You will have an isomer in which both methyl groups are on the same side, and there is another isomer in which both groups are on opposite side. So this could be the trans isomer and this could be the cis isomer. To draw the flat structure, we look from top. So looking from the top, these methyl groups going away from you, so that's why we use a dash bond here. Looking from top, this methyl group is coming toward you, that's why we use a wedge bond over here. So you could see wedge and dash that this is a trans isomer at position 1, 2, 3, 4, 1,4 trans dimethyl cyclohexane. Same thing over here, 1, 2, 3, 4, both on the same side, cis 1,4 dimethyl cyclohexane. These two are stereoisomers because they are not the mirror image of another, they are also diastereomers. If we're asked to draw the most stable conformation of trans 1,4-dimethyl cyclohexane, what I suggest you to do is draw a chair and draw all the bonds. The rest of the bonds are not shown here, but I can say that the positions that are trans in this carbon and in this carbon are this equatorial is trans to this equatorial to opposite plane, and this axial will be trans to this axial over here. Because obviously you want the bulky groups in equatorial, you can see how this conformation is the most stable in which both methyl groups are di-equatorial. So the most stable conformation for trans 1,4-dimethyl cyclohexane is the trans isomer, okay, in which both groups are in equatorial position. For the cis 1,4-dimethyl cyclohexane, we have both groups on the same side. In position 1, we have an axial going up and an equatorial pointing down. In position 4, we have an axial pointing down opposite and an equatorial pointing up. So if we place the one methyl group in the equatorial, which is up, to be trans, okay, to be cis. So if this is equatorial pointing up to be cis, the methyl group here will have to be in axial. If we place the methyl group in axial here to be cis, it will have to be in equatorial. So basically, both chairs are the same energy. That's why there is only one drawn over here. Because in both chairs, the amount of 1,3 diaxial interactions is the same. In this chair, we will have 1,3 diaxial interaction with its axial. In the flip chair, this one will go axial and it will have also the same amount of diaxial interaction. So there are examples in which both chairs are equivalent and both you have substituents on the cyclohexane. So here is an example. So here is the same example that I said. When you have the trans isomer in a chair, both isomers are in axial position, so there is a lot of 1,3 diaxial interaction here and a lot of 1,3 diaxial interaction over here. In the flip chair, this comes up down here. Anything that is axial goes equatorial. This one comes up, axial here goes to equatorial. So clearly, in the trans isomer, there is a chair conformation with two bulky groups will be in equatorial position. So that would be by far the most stable chair conformation. You can look it over here. Okay, you can see the interactions here. In the flip chair, in the cis isomer, I'm sorry, you have in one chair, because they are cis, they are on the same side. One methyl is axial, one methyl is equatorial. So there is 1,3 diaxial interactions over here. There is none on the other one because the other methyl is equatorial. Bringing this one down, this equatorial to axial, bringing this one up, this axial goes to equatorial. And now is the reverse. One bulky group is in equatorial and the second one is axial, having 1,3 diaxial interactions. Because the amount of 1,3 diaxial interactions is the same in both isomers, we can tell that this cis-1,4 dimethylcyclohexane will be in a conformation in which 50% of the molecules are in this chair conformation and the other 50 will be in the flip chair because they do have the same amount of energy. Finally, I wanted to mention here, and something that you have seen already in the online homework, what we call bicycloalkanes. So bicycloalkanes are alkanes having two cycles. Usually, these two cyclic structures is a result of one carbon bridge in between carbons. In this case, the bridge is in between carbon 1 and 4. That's leading to two cyclic structures, 1, 2, 3, 4, 5. And the other one could be 1, 2, 3, 4, 5. Okay? Here is another example. Same thing, but in a different conformation. Okay? So whenever you see bridges in between carbons, that will lead to bicycloalkanes. And one of the most widely seen bicycloalkanes is adamantane, in which basically you have this conformation here. This is the compound. And in the compound, because these three groups are bonded by one CH group, the compound is basically forced into this conformation. This compound, which is called amantadine. Amantadine is basically one used a drug as an antiviral agent. So you guys need to know how to name bicycloalkanes, which, as I said, is an alkane containing two rings that shares two carbons. And there are basic rules to name bicycloalkanes. They're pretty simple rules, and you guys should read this in the text, but I'm going to go over this in details, okay? You will have also a couple of videos on the homework to learn to name bicycloalkanes. It's pretty simple, as I said. Well, with that being said, guys, I'm going to stop this video and hope you guys learn from this small lecture the conformation of cycloalkanes and stability of these conformations, as well as cis-trans isomerism in cycloalkanes.